Okay, I'm going to go over a couple of proofs for negative binomial distribution, a bit like I did for the geometric. We'll just do total probability and expectation. The proof for variance is similar, it's just longer again. But again, I'm happily go through it with you if you'd like to see it, or you could work it out yourselves. So if x is negative binomial, p probability of success, r is the number of successes you're after, then the probability x equals r, that should say, that is right, probability x equals x, so it's the number of trials until you get r successes. This formula here, the smallest number of trials will be r, and then we increase by 1 each time as we go along. So x can be r, r plus 1, r plus 2, r plus 3, and it's an infinite distribution. So all the probabilities need to add to 1. So if we start with letting x equals r, then we can think about the probability that x equals r. And so I'm plugging into here, essentially replacing x with r, actually. So you get r minus 1, choose r minus 1, p to the power of r, and then q to the power of r minus r, which is 0. This here is going to give you 1. So for instance, if r is 5, you would have 4, choose 4. There's only one way of choosing 4 from 4, and that's to pick all 4. And so that's always going to be 1, because you've got the same top and bottom here. And q to the 0 is 1, and so this is equal to p to the power r. If I now let x equal r plus 1 and find the probability that x equals r plus 1, then plugging into the formula, you get r choose r minus 1, p to the r, and then r plus 1 minus r gives you q to the power 1, which is q. R choose r minus 1. So this is, say r is 4 again. If you've got 4, choose 3. You're always leaving 1 out. You're choosing 3 from 4. And so 4 choose 3 is going to equal 4. And r choose r minus 1 will equal r. So we end up with r, p to the power r, q. Next one, if x is equal to r plus 2, so we want the probability x equals r plus 2, and again feeding through that formula, we've got r plus 1, choose r minus 1, p to the r, and then we end up with q squared. So to sort out this r plus 1, choose r minus 1, I think we're going to have to use a formula. So the formula for n choose r is trying to get them around the right way, n factorial over r factorial n minus r factorial. So plugging into there, the top of this, if it's r plus 1, choose r minus 1, I've got r plus 1 factorial over r, which is r minus 1 factorial, and then n minus r is going to be r plus 1 minus r minus 1. R minus r is 0, 1 plus 1 is 2, and so that gives me 2 factorial. And then the top of this fraction here is equal to r plus 1 times r minus 1 factorial, and underneath I have r minus 1 factorial times 2. So they're going to cancel off, and you are left with r plus 1 over 2 factorial. And so this next line here, I end up with r plus 1 over 2 factorial p to the power r q squared. And then you could keep going, but we'll leave it there, but that would continue. And then what I'm going to do is I'm going to pull out the factors. So the sum of the probability that x equals x from x equals r to infinity is this lot added together. I've got a p to the power r in all of them that I can pull out, and then I end up with 1 plus rq plus, I'm just pulling out this p to the r plus 1 over 2 factorial q squared plus, and then you would get a pattern emerging from there. If you look at what we've got here, this is exactly the same as one of those questions I put on your lesson starter. So that is the same as this here, which is 1 minus q to the power of minus r. So I can replace this series expansion. You may want to do a couple more terms just to see that pattern for sure, but I decided 3 was enough. So p to the r times 1 minus q to the power minus r. And 1 minus q is equal to p. So this is equal to p to the r times p to the minus r, which is p to the power 0, which is equal to 1 as required. So that's a proof that all of the probabilities add to 1. I just think it's good for you to see these proofs, and also it makes you realise why the negative binomial distribution is called the negative binomial distribution, because you're expanding a binomial expression with a negative power in there, and you'll see that happening again when we look at the expectation.